I'm glad to welcome you all to the webinar today. I would like to introduce our speaker, Seymur Gurbanov. He is an engineer, completion engineer at Schlumber. He has over 8 years experience of industry. And today he will present for us his case study on the topic of scent control and selection technique. Please, Seymur.
So, good afternoon, everybody. So, I will start with the presentation. So, my idea in this presentation is to give just maybe the introduction to some control selection, because this topic is extremely huge and that will require a lot of review and quite subjective. By saying subjective, that's mostly depends from the different well environments, different conditions. So this is just to generally introduce the sound control types, I would say. So the agenda is to start with the standalone screens. So how the screens should select it, what influence selection, and in which cases you may have the problems. So then the gravel pack, a little bit about the gravel pack. So what's the gravel pack screen selection criteria, and what type of fluids we have, and each type of the gravel packs. So there is the different ways to gravel pack the same well. And then just a little bit about the sand retention test, how it happens, why it's required or mandatory even. So everything starts with the PST test, which is famous. Everybody knows how it is. So you just taking the core sample. Here we mandatory to mention that core sample has to be representative. So normally that means you have to take core sample from the reservoir section where the oil will produce by itself. The produced sand or from somewhere else will not properly give you what you have in the well, can could be the problems during the well production. So the main criteria is what we're taking out from the PST test is the T50, so select the average sand size. And there is the sortage and uniformity coefficients as well. So they are quite critical. The D40 over the D90, this one, identifies the uniformity of your sand. So the sand, it varies in the wide range. So the smaller and big particles have the big difference in sizes. So standalone screen may not be so efficient as we want to. So that's why we need to look to the other options. So here is just the D40 over 90 if that in between the 1.3 to 1.5. So that's quite uniform. So that means the biggest and smallest particles are not varies from each other much. So uniform formations. So it's the mid-range of the uniformity is something less than 3, and poorly sorted is above the 20. So in reality, you may be faced with the case where you have the more than 20 uniformity. So poorly sorted formations. So what it gives us? So from the beginning, the first method of the selecting the screens for the standalone options was discussed in the SPEs by the Coberly in 1937. So he recommended to use the 2 times of the D10. So the D10 means the biggest particles. So the first 10% of the biggest particles, you're doubling the size, and eventually you have the sizing of the screen which you need to install. But in practice, it doesn't work out so well. And in future, by another researcher in 1985, it was advised to use the same size as a D10, so the biggest particles which we have in our PST or the formation. So that option also works. In reality, there was several issues with that. So here you could see the chart. where it was represented like the mesh size, manufacturing size, which they identified as the size of the screen, versus the D10. So as you could see, the main criteria, over here is if the size of the screen is 3 times bigger than the biggest particles in your PST, so you will have the severe sound production, which goes to the higher numbers. Versus to the what you will have is when you're sizing close to the D10. So when you have the close to the D10, your sound retention is quite fine. So you're producing relatively sounds free because the acceptable range is something below the 1 pound per square feet. But the results, as you could see in the beginning, you have the sound production, and in later stages, as long as your screens get it formed with the filter layer of the formation sounds, you're retaining more and more sounds, and eventually you will have the small amount. But when you're going below to the lowest one, 0.78 times of the D10, you will see that there is the intermitting behavior. So that means your bridge is forming over your screens, and in some point it fails, and then forming again, which is not good as well. So your formation doesn't behave in a stable manner. So later, it has been developed more scientific or the more advanced method of selecting the screens for the standalone options. So Marquestad has developed some sort of the criteria. So you have the 4 different groups of the sizes, and you just defining them through the PST tests. So you're taking the sample, passing through it your formation fluid or the viscous fluid, and you're defining that's the D double minus is defining the size of the screen where your screens severely plugging. So that's your critical bottom line, and you have the D double plus. After that, if you select the screens bigger than that, you will have the producing all the whatever you have in the formation. So the continuous sound production, they call it. So they are the sizes which you need to avoid. They are your critical sizes. So he have developed like D minus and D plus. So that's as you could see from here, the smallest slot size were not plugged, and the largest slot size where the sound is not producing. So the green zone in middle, that's in between the D minus and D plus. So you have some range of the screens. Sometimes they both have the same number. As you could see here is from the SP paper. So as you could see in some cases, or even in most cases, you have the very similar sizes. So here is a D minus and D plus. So in most cases, it's very close. In some cases, there's a range. So you could vary within that range. And to select, you may select in this case the 200, 300, or 400 microns, whichever satisfies your need and the production rate and so on. So you're evaluating based on your formations. So what's the new model of the simulating and founding the screen sizes? Because doing the PST tests are quite complicated. They are costly. So at least before doing the test, you need to have some understanding of the water size to test, at least, because without knowing the certain directions, you may end up with 10 or 15 tests which are consuming your budget. So the new model way of the thinking is that when you're selecting so here is the wires, and you have the gap opening in between. So the assumption is that any particles which is enough big of that gap will stay on the filter, and anything smaller than that size will pass through the screen. So special calculations has been run to identify that how many sound will pass through the screen till to the point when you have just one layer of the big particles covering your screen. So now what happens, you just calculating how much sand will produce for this size of the screen, let's say. So running this calculation gives you you will have 100 micron and how many screen of sand you will produce. Or if you will have the 200 microns, how many sand you produce. Eventually you have the numbers like the pounds of the sand per square inch of square feet of your screen surface. So basically you know how many sands you will produce for this length of the open hole. And later you just evaluate which quantity is acceptable for you, and you just select that size. And later you passing through the PST test. So basically these calculations or this simulation gives you digitalized sand retention test. So basically you just doing the calculations and you have the result of calculations. So it says the 100 micron will produce such amount of sand, 200 will produce such amount of the sand. So you have selected what you're interested, and then you have to test it. Or if you have some problems or you don't want to spend the money on the test, you could run the field trial, no. But at least you will have some justified sizing. So here we have the two different scenarios, because the formation could fail as soon as you will produce the sand. I mean, you open the well to produce the oil and formation could fail directly to the filter cake, could fail to the screen, and you will have this condition, which described as a prepack. So on that case, so your screen will be plugged faster, so you will produce less sand. Or you could have this slider option when your formation fails gradually while you're producing the fluid brings some quantity of the sand from formation, and that creates the bridge. But since the sand comes not all in one time, so you will produce more sand. So the same type of the calculations exist for the wire wrapped screens, because the selection of the screen type mostly depends from the client. So for the wire wrap screens, there is the bit variation. So the particles which are bigger than the slot opening. Slot opening, I mean the distance in between two wires. The particles which are bigger than the distance between two wires, they will stack on top of the wires, and the particles which are smaller than that will pass through it. So again, the calculation will run to calculate and gives you the understanding of for this 100 micron, you will have, let's say, 0.1 pound of the sand. For the 150, you will have the 0.15. So you're selecting based on that information. Here also we have the two cases when you have the slurry. Slurry means your formation produces gradually with sand, so sand covers your screen by time. But prepacked means like when you open the surface to produce the fluid, the open hole will collapse on the screen. So prepack option is every time gives you better results. Slurry options gives you bit worst, I will say. So it's purely up to operator to select which option to go. Most of the times people are oriented in our industry to go with the worst direction. So most of the time you will look to the slurry options, because you never know open hole will collapse gradually or just in 1 second. So this is the new way, let's say, approach to the selection of the screens. So now you're not linked to the just one number, D10, because when you are renting to the one number, so you have the D10 over here. But what about the remaining parts? If you have a lot of the fines, so you will produce so much small particles which eventually may erode the screen. As well, the offshore, it's very critical to control how many sand you will have on surface, because you have to separate it and dispose that sand. If you will accumulate a lot amount, so you have to spend to the vessels and so on. That's why offshore companies are very keen to control these parameters. So eventually we come to the selection criteria, how you select the gravel pack or just to have the standalone screens. Here, as I said, there are three critical parameters: the fines, or the particles which are small enough to pass through the screens. So they are the 44 micron or smaller. Uniformity, which means how difference is between your small and big particles. And there is the shortage coefficient as well. So based on these three parameters, you may decide what option to select, to go with the standalone screens or to go with the wrap screens. So here you could see that with the fines about 2%, the recommendation is to go with the premium screens or the wrapped. But the fines goes above the 5, close to 5, so the recommendation is the premium only. That's because there is the general belief in the industry that the wrap screens are plugging more easier because they have just a one slot opening, and if you plug that slot opening, that's it. For the premium screens, you have the several layers, and that gives you the flexibility because you're creating the bridge through the different layers, and even if you will plug the certain amount of your perforated holes on the screen, you still will have some others to remain. That's why the premium screens are recommended when you have the more fines. So anything above the 5% fines and with the really bad shortage, so it means that the range of the size particles which we have in the formations varies a lot. So the gravel pack is only recommended. Gravel pack in reality proves his efficiency, but have several disadvantages. They are the complexity, cost, and efficiency sometimes, because if you haven't properly planned the gravel pack, so eventually you may have problems. So here's how you select the gravel for the gravel packs. So as soon as you did the PST test, so you know your D50 number, and Saucier method is widely used for the gravel selection. So that says you just take your D50, multiply it by 6, and you will have your gravel size recommended. So as soon as you will select the gravel, you may select your screen. So when you select the screens slots or the screen size has to be the half of the smallest gravel which you have. Here is the example of the 2040 gravel. So for the 40 gravel, the half will be the 0.008, or normally we will call it the 200 microns. Here is the explanation of why the cesium method is best among all others. Here is as you could see, the multiplication of the D50. So when you have the multiply by 6, you will see that the gravel pack permeability is high. That means when you have let's say, close to the D50, you will plug partially your screen, so your permeability will go down. If you will have the gravel size bigger than the 7, 8, or 10 times, so again, you will have the reduced permeability. And if you will have the 10 times of your D50, so basically your gravel will not stop any sand. So all the sand which comes from formation will pass through. Here's just bit elaboration on the gravel packs. So you select the gravel to stop the sand from formation to produce, and you selecting the screens to stop the gravel from being produced. So here's the regular completion configuration for the gravel pack. As you can see, there is the screens along the open hole. There's a blank pipe that's to space out the packer and accessories from the screens during the screen out while you have the gravel pack. So screen opening has been designed to stop the gravel. Gravel has been designed to stop the formation sand. So here I have the two animations to show two main ways of the gravel pack. So the most famous and most cost-effective, I will say, is the water pack or the circulation pack or alpha beta packing. There are different names for that. So basically, you're just using the water brine or the Newtonian fluid to carry your gravel. So the thing is that as soon as your fluid slurry it's a mix of your brine and sand, opens the open hole sections, it starts to settle on the bottom. So industry calls it alpha waves or the first wave. So the sand starts to settle to the point where you have the channel, which is tiny enough that your fluid flow is turbulent, so the sand will not settle anymore, and it will bring the sand to the wider areas. And then as soon as you have packed the alpha wave is over, then the beta wave is formed. So the gap above the first wave is covered by the beta wave, where your pressure is going high because your area of the opening for flow is reducing to the point where you don't have any area to flow back, and your pressure spikes. So that's called the screen out. So that means all the screen section has been covered with the sand. So the bad side of this technique is that if you have the damage on the filter cake, for some reason you will lose the fluid to the formation, you definitely will have the gap or the void space where you don't have the gravel packet. So that's also a problem because you could have the sand erosion, damage, or some other issues. That's why the second way of the gravel pack has been developed. This is the viscous fluid which used as a carrier. So more advanced thing with that viscous fluid is that they use the alternative pack systems. So you have the special tubes above the screens. So when the area around the screens has been covered, you still have these tunnels through which your gravel will pass and go fill the places where you have the voids where the gravel is not settled because of the different reasons it's made. So you cover from the failures. So if you will have the issue with the open hole, you still will pack all your open hole. With the pack, that will not the case. So let's run the animation. So in this case, so the light gray means that's the mix of the carrier fluid and the sand. So it's not packing, it's just the slurry or the mix of the fluids. So at first it's start to fill entire sections. So in this scenario, we have described the failure. If you will have the loss in certain sections, so you will pack all the zones above it, but not the below. So the advantage of the system is that as soon as you complete this, so your tunnels to which the gravel still may travel will pack all the remaining part of the open hole. So this gives you a guarantee of full packing, and with the guarantee also comes the cost. So the last one is I want to talk about the sand retention test, which is very critical and most of the times underestimated. So sand retention test basically gives you a good understanding of what will happen if you will run these screens, let's say 100 micron screens. So instead of running the compilation, producing the well for 1 year and then analyzing the results, you will have just one test, which will give you a good understanding of what in reality you will have. So you will save the money, avoid the failures, and the cost of this test is relatively very, very small. So disadvantage of this test include in that there is no unique or API standard how you need to do this test. So it's very subjective. So everybody decides for himself how to test it. So somebody thinks this way is the smart, so he doing in that way. Somebody thinks another options. So everybody selects their way. So basically, what is common in all this, there is the sensor below the screen and sensor above the screens to measure the pressure. You have the test screen in between. You may have the gravel if you're planning gravel pack. If you don't plan the gravel pack, you may have just the formation sand on top, and you're just passing the fluids through it. You're measuring the time, how long it takes, so how many protons has passed, how many sand has been produced, and so on. The difference in between these two tests is just the end shape. So here you see the cone, because the cone will not allow your sand to be trapped. In this square shape, your sand may be trapped in these corners. However, if you have the conic shape, all the sand which passes through the sand will, by gravity, will fall to your test cup. So you will see in reality how many sands you have produced. So normally the results looks like on the right of your screen. So you will have the screen port size rating. So you have the sand, what's your D10, D50, D90. The screen thickness, what's the thickness of the screen, is screen porosity, initial screen permeability, and what will be the remaining permeability. So it gives you the good understanding how many your permeability is damaged across the screens. As well, it will give you what's the D10 of the produced sand, means the top 10% of the biggest 10% of the sand which you have produced. So, and how many solids? So here you have the pounds per square feet. So you know how many propant you will produce if you will pass the 3 gallons of fluid per square feet. So you could calculate for your well conditions how many sand you will have if you will select these screens. So you know what's your production rate expected and so on. So here is just a general guideline how to select the best candidate. So any screens which will give the 50% or greater retained permeability means your screen is not plugging, which is good. So maximum produced solids D10 is below the 50 microns, so you're not producing the big particles. The issue with the big particles is that the big particles have the big energy while hitting the walls of your tubing, surface equipment, and so on. So the particles below the 50 micron has the less erosion severity in comparison to the bigger particles. And produced solids, so these numbers are really subjective. So every sub-client, every operator of the field decides for himself what to select. So you may see somewhere the bigger number because that's the land rig, maybe they have some other preferences. So this is again very subjective to select the screens, and any selection has to be justified with the sand retention testing. At least one test should be done to be confident on what you have selected. So that's all from my side. I will gladly answer your questions. Hope you enjoyed the presentation.
Thank you, Seymur, for the great presentation. So we have some questions in chat. Can you read it or?
Which simulation software has been used to conduct this study? Haris from Pakistan. So Schlumber has its own, let's say, the web-based software. That's name is the Sand Advisor. So basically, we inputting the PSD test results, and it calculates based on the equations which are from the SP justified. And so it gives us that quantities, so we know how many sand we'll produce. We know what is our cut line, so we know that's above but the number which I show you here, like the 0.12 pounds per square feet. Actually, that's valid for the gas wells. For the oil wells, since the oil produces with the low velocity, that number goes higher. So in oil wells, that's the 0.5. So the Sand Advisor, yes, it spells like as you write it. So, and you may calculate by your own. I guess the big companies, the Halliburton, Baker, also have their own softwares to calculate it. So there was another question. I hope I answered your question. What method is described in slide 9? So let me check what is in slide 9. So this is the Saussure method. So there is the SPE related to that. So same method is widely used. So I guess everybody in the oil industry refers to that method. So what he have done, he has selected the different size of the gravels and come out to this plot. So this plot is just basically shows you that when you have the part gravel small than the D50, let's say the gravel size and the D50 ratio is between 0 to 5, you have some sort of a plugging. If that's above the 6, also you will have some small plugging. But if you will select something above the 10, so you just producing the sound continuously, nothing stops basically. I will give you the name of the method. Be clear, so I need to find the spelling of the name. I'm a bit lost. So what was the next question?
Yeah.
It's Sound Advisor. Yes. What method is useful for online monitoring of sound entry in the wellbore? What's the method of is used for online monitoring? So there was, let's say the monitoring. There is a tool. I'm not sure how they call it in the English. So there is a special tool which measures the sounds. So it refers that's the sound which enters the wellbore, hits the walls of your tubing, so creates the noise. And there is a special tool which measures that noise and says you how many sound passes through that tool. So most of the time it's installed somewhere on the surface. So the oil which comes to the surface passes through that tool, and that measures how many sound you have in the cubic meter of your produced sound. So that's the one method. But if you're talking about the method to see it on the bottom hole condition, there is the two ways. There is the wireline tool, which doing the same. So it measures the sounds created by sound which hits the metal. So you're running the special tool and you just passing across your intervals, and the zone where you have the sound hits that tool, and that tool registers from which interval exactly you have the sound produced. But that's there is another way is the video monitoring. So you have the special tool, but that's complicated because you have to clean the well very good. So you have the clean brine inside the well, so that camera will be able to record and see what happens inside the wellbore. So you may identify where you have the leak. For online, what does it represent to chart on the rig? Right of slide 7. So another question is slide 6 and 7. The right one is modeling. So when you have the pre-packed screens, so the calculations which you apply, it counts the particles which passes through that packing. So this is the discrete element analysis. So that is done through the simulations, and there is a special equation to calculate that as well. So these both, the left and the right, has been represented in the same SPE papers, which I could share the number, but a bit later because I need to search the SPE paper's name. So here is the same. So there is actually two papers. One is related to the wire wrap screens. Another one is for the single layer premium mesh screens. So within same present SPE papers, it describes the way if you will have the slide producing, so the sound comes partial, or you have the pre-packed failure. So there is another equation to count the particles which passes through this opening, and based on that particles count, you may decide what screens is acceptable. So you can convert that quantity of particles to the weight because you know the density of your solids which produced. So it gives you your same results for the different cases. Big companies for methods speaking companies were controlling sand in Caspian Sea oil and gas fields. So BP has started, when they just started to produce from the ACG, they have tried different ways of the sand control. So starting from the just the screens, standalone screens, expandable screens they have run the prepacked screens as well. So eventually what they come is the gravel pack is the best fit option for the ACG fields. So they are gravel packing all the open hole wells. With the cased hole, they are not using the gravel pack because the gravel pack adds some mechanical restriction to the fluid flow. So they are trying to maximize their production. That's why for the cased hole completion, they are not using the gravel pack. But for all the open hole completions in the Baku are with the gravel pack. Yeah, they have used expandable screens. I don't know when it was exactly, but they concerned about the results because the expandable screens are not good on the lateral forces. So eventually they had the bad results from the well. I couldn't recall exactly what was the issue with that because after a certain time, I guess they had the increase on the sand production. So another question is, what method is better for sand separation when we use sand filter at the surface or when we have the filter at the bottom hole? So for my personal understanding, when you have the separator on the surface, so your fluid travels all your way through the upper completion, through the wellhead to the separator. So eventually you will have the erosion all the way up to the separator. And if the quantity of the sand is huge, so you will have a lot of sand on the surface, which you need to dispose. So there is another issue because when you're producing the solids comes from the formation. So the sand productions in the literature says like that, producing on this load-bearing sands. So which means you're removing the particles which takes the part of the load. So you have the cavities around your casing and eventually you will have the tectonic movement or the collapse of your open hole just because you have the void space and your formation is not able to withstand that lateral forces. So you may have damaged your lower completion. What about the borehole, downhole, and separation? So how about the borehole monitoring and controlling by BP? Borehole down. I'm not sure on the question. How about the borehole monitoring? I guess there is no borehole monitoring unless, okay, there is the technology which exists. They call it the optipad, optic cable around your completion, so it's able to register the noises and give you an understanding of how many sounds from which interval comes and so on. But I guess they are in development phase, so they are not fully implemented so far. I know that's our reservoir monitoring and control department working on that. So I guess within the next year probably that will come commercialized and later we could talk about that. So does Schlumber have downhole sand separation technology? So downhole sand separation, I do not really imagine how it may be. I mean, the sand separation is the filters for my understanding. So you have the filter and fluid while passing through the filter or the screens. The sand stays and fluid passes. So you're separating your fluid and solid phase. If you're talking some kind of the turbulent flow where your sand will separate, but the sand has to go somewhere. So it will settle inside your well bore or drop to the shoe. So eventually it will build up to a certain level when it will create problems. But so far, I'm not sure about any other ways except the screens. it's good presentation. I don't know the question. What are the factors that influence the erosion of tubing due to sand? So the erosion by itself is quite complicated, and most of the times you will need to have the CFT analysis or discrete element analysis to twin together to simulate the real cases of the erosion, because you need to find what particles comes in and how they hit the walls. So the best way to control that erosion is to avoid the sand production at all or minimize it. So that's the best, because you couldn't live with the sand producing. That's not the way. Even if you will manage to the sand erosion, if you will manage that the excess amount of sand which you have on the surface, you will somehow dispose them. But in the wellbore, you're losing your solids. So you're losing your formation and you're generating the cavities. And normally everything goes back to the physics. So you have the weight affecting from top, you have the lateral forces, and all this is balanced when you're drilling the hole. After the certain amount of solids are produced, that balance is lost. So your forces is not balanced anymore, and they will try to find a new balance, which will generate another movements, the collapses. So you could damage your screens if you have them. If you don't have the screens on the hole, so you have just a bare hole, that even worse, you may collapse your open hole, so you will lose your production from entire zone. Field in Iraq, we have sand filtered and they will better. So here's the interesting questions. In our field in Iraq, we have a sand filter and the wellhead after this Christmas tree. It's not better to pour the filter at the hole. I mean, going to the sun due to the tubing and other equipment until the wellhead is not damaged is equipment in the future. And to be honest, I didn't get the question. Our field in Iraq, we have the sun filters at the wellhead after this Christmas tree. It's not better to pour the filter at the bottom hole. Okay, I mean going to the sun due to the tubing and other equipment until the wellhead is not. So I didn't get the question properly, fully I will say, but as I understood, you have in your field the sun separator after the wellhead. Okay, I mean, the important thing is you need to analyze case to case. Maybe you have the sand, but that's manageable. So there is no excessive amount of sand. There is the amount which is less than the, let's say, 1,000 pounds per month. So that's a really small amount. So you could live with that, just manage after the surface. But if you have the excessive sand production, excessive means you're producing a couple thousand. So definitely on that case, you have to think about the erosion risks, and you have to think what to do to improve your well life. In which cases the gravel pack can. So gravel pack itself creates the mechanical restrictions. So you're adding to the system another restrictions, which elevates your skin factor. So if you properly selected the gravel and so on, your gravel pack will just have the +5 skin. So it's not much, and your production will be just reduced in comparison with the open hole production. But if you will select in the wrong way, and you selected not based on the social method. Now, basically, everybody orients to the social method. The problems comes how the people doing the PST tests. So instead of having the core sample from the producing zone, they had on the surface. So the formation produces, you have the solids coming to the surface, you're just taking the some portion of that solids, and you're doing the PST, and people think they did the right way, so their screen will work. But in reality, you have to take the core sample, because not all the solids come to the surface. At first, some settles in the wellbore, because of velocity and so on. As well, there is another issue that when the fluid comes through your wellbore, they could separate to the, and on the surface, you are not taking the real sample of what comes in each liter. You're just taking the wrong results, wrong gravel, and even you will have a lot of product damage the reputation of the gravel pack most of the times. People's doing in the wrong way, and then they blaming that the gravel pack doesn't work. If properly selected, gravel pack will work. So this technology has been developed 80 years ago, and so far humanity haven't developed something better than that. Maybe in future we will have some better solutions, but for now it's like that.